Good day, everyone. Welcome to another lecture in the series Medicinal Chemistry 1. And today we'll be talking about adrenergic receptor antagonists or blockers. All right, so as I mentioned, we'll be looking at blockers, right? So we'll be looking at our alpha blockers as well as our beta blockers. And then we'll be looking at their structures, and then hopefully we'll be able to look at why one is non-selective versus selective to a particular receptor. So the first group that we're going to look at is our alpha blocker. All right, so the alpha agonists cause vasoconstriction and raise blood pressure, right? And so the blockers should be therapeutically used to be an antihypertensive agent, right? So if our agonists raise blood pressure, then our blocker should do the opposite of that. So these are some examples of some alpha blockers. So we have tolazolene, which is non-selective, phentolamine, which is non-selective, and we're looking specifically at phenoxybenzamine, which is an irreversible non-selective alpha blocker. And then we have some azosins as alpha 1 blockers. So this is the mechanism of inactivation of alpha adrenergic receptors by our beta halo alkyl amines, right? So as I mentioned a while ago, phenoxybenzamine. So let's go back to it. Here we said that it's an irreversible non-selective alpha blocker. And so we're showing here the mechanism by which it inactivates the alpha adrenergic receptor. So let's look at the structure, right? And so we have a beta halo alkyl amine, which means therefore that our amine is the base here. So in both of these, we have nitrogen at the center, which is clearly a tertiary amine, right? And so we have the halo in the beta position. So we have the nitrogen, then alpha, beta, and then halogen, right? So that is why it's a beta halo alkyl amines. I didn't mention the alkyl, but the alkyl portion here, right? So we have a tertiary amine, as we said, and we have the halogen at the beta position, beta to the nitrogen group, right? And so this is an oversimplified structure of our beta halo alkyl amine, where the R1 represents, it could be this group here or this group here, and then R represents the other group that the nitrogen is attached to, right? So everything else should be the same. So this is a drug, right? So it forms a three-membered ring, as we can see here. So the lone pairs on the nitrogen will attack this electrophilic center, this carbon here, causing our carbon chloride bond to break, right? And so we end up with our chloride ion here and a three-membered ring, and clearly our nitrogen would have a positive charge because it now has 4 bonds, right? And how it interacts with the receptor is that we have our receptor here, and it has a nucleophilic portion which will now attack our ring, which is a strained ring, and so it would be susceptible or easily broken up, right? And so our nucleophile can attack this center, causing our carbon nitrogen bond to break and therefore quenching this positive charge. And so we end up with this irreversible bond between our receptor. So now we have an alkylated receptor. So again, just to reinforce, it's an irreversible non-selective alpha blocker, particularly phenoxybentamine. And this is the mechanism by which it binds irreversibly to the receptor. All right, so let's have a look at some selective alpha 1 blockers. And we mentioned the azosin, so the terdoxazosin and the priazosin. And so we have our structure here. This is the basic structure, which is a quinazoline ring seen here. We have our piperazine ring here, and then we have our acyl moiety, and then the R represents these cyclic structures that are oxygenated, right? And so these structures or these compounds are selective alpha 1 blockers. In comparison to our selective alpha 2 blockers, now different structures, right? So we have this cyclic 1, 2, 3, 4, 5 ring structure here. And the only difference between both, as we can see, everything matches up in terms of well, most things match up. The only difference is this chiral center here, in which this ester group, so we can see here that it's a ester group, is in opposite stereochemistry, right? And so yohimbine and corinthine, right? That is the only difference between both. That's the difference in stereochemistry at that chiral center there, and that makes one a selective alpha 2 blocker and the other a selective alpha 1 blocker. So that leads us now to our first question, which is, what are beta haloalkyl amines and how do they inactivate alpha adrenergic receptors? So pause, try to attempt it from memory. All right, so these are our beta haloalkyl amines, right? So we have our R groups attached to a nitrogen center. We have our alkyl portion, and then we have our halo, which in this case is chlorine, right? And so the first carbon would be alpha, the second one would be beta, and then we have our chlorine here, right? So this is our beta haloalkyl amine. And then the other part says, how does it interact with your receptor, right? So we start off with our beta haloalkyl amine, and then the lone pairs on the nitrogen will attack our carbon here, causing our carbon chloride bond to break. And so we end up with a chloride ion and this 3-membered ammonium ion. And so our nucleophilic portion of our receptor will attack our carbon of the strained ring ammonium ion. And as a result of that, our carbon-nitrogen bond will break and quench a positive charge. And then we end up with this irreversible bond between the receptor and the drug. Or follow-up question 1 is, compare the structure and activity of yohimbine and corinanthine, and so ensure that you have that answer prepared. All right, so the next thing that we're going to look at, or the next group, is our beta blockers. So our beta blockers are among the most widely employed antihypertensives and are therefore considered the first line of treatment for glaucoma. Sorry. And most of beta blockers are in the chemical class of aryl oxypropanol amine, right? So whenever we see a class of compound, we should always try to look at the structure to see how it breaks down. Where is the aryl portion? Where is the oxy portion? Where is the propanol portion? And where is the amine? So let's do that quickly. Let's use propranolol. So we have our aryl portion. We have our oxy portion. We have our propanol. So we have 3 carbons here and a hydroxyl group. So we have our propanol portion and we have our amine portion. So as it said here, most of the beta blockers are in the class of aryl oxypropanol amine. And you know that I like to talk about my history. So the history in terms of who started or discovered the first type of this particular drug. So the first beta blocker is DCI, which is dichloroisoproterenol, and it was reported in 1958 by Powell and Slater. So this is a structure of DCI, and what should ring a bell at this point is isoproterenol, right? So it's the dichloro part which might throw you off, but this part should ring a bell. So this is the structure of DCI here, and as I said here, it's a partial beta agonist. So though it's a beta blocker, it's a partial beta agonist as well. So as I said before, we did look at isoproterenol, and that is why it should ring a bell. So the only difference between that, and I think we're even going to reinforce it later on, is that we have 2 chlorine groups here where the hydroxyl would have been for isoproterenol. So as we go forward, we're going to look at these beta blockers in a little more detail. All right, so for DCI, it differs structurally from ISO and isoproterenol in that the agonist directing 3,4 dihydroxyl groups have been replaced by 2 chloro groups, right? So for isoproterenol, as I said before, where the chlorine is, it was OH. And of course, that would be a catechol unit, right? So hopefully that rings a bell as well. So this simple structural modification, just replacing the hydroxyl for chlorine has provided the basis for nearly all of the approaches used to subsequent efforts to design and synthesize therapeutically useful beta blockers, right? So this is the model. This is the model to synthesize therapeutically useful beta blocker just by replacing the hydroxyl group with a chloride has given insight into other beta blockers. So beta directing tert, butyl, and isopropyl groups are normally found in the amino function of the aryl oxypropanol amine blockers, right? So we're talking about this part here. And for DCI, this would be an isopropyl group. And for other beta blockers, this could be a tert butyl group, right? it must be a secondary amine for optimal activity, right? So we must have two R groups for optimal activity. So the isopropyl here and it being attached to an R group here as well, it is therefore a secondary amine, and that is important for activity. All right, so for aryl ethanol amine adrenergic agonist, the beta hydroxyl substituted carbon must be in the R absolute configuration for maximal direct activity, right? So you know all of this already. However, for beta blockers, the beta hydroxyl substituted carbon must be in the S absolute configuration for maximal beta blocking activity. So as we have seen with our neurochemicals, right? And we see where the R configuration was important for agonist activity. We're seeing here where the S absolute configuration is important for blocking activity. And these are specific to our aryl ethanol amines, right? So let's break down the name again. So we have our aryl portion, which is our aromatic ring. We have our ethanol portion, which is 2 carbons, right? And our hydroxyl, so that is our ethanol, and our amine portion as well. So here clearly we can see our ethanol amines here, aryl ethanol amines, and below we have our isopropanol amines, right? So let's break down these classes and learn the differences, right? So for these types of structures, we're saying that hydroxyl, for it to have blocking activity, the configuration needs to be S. Okay, so that leads us now to question 2, which says distinguish between DCI and ISO. So clearly for a question like that, you want to draw the structures, right? So this is ISO, if you recall, and this is DCI, right? So the only difference, yes, we have drawn out the isopropyl here, but it's the same thing here, just a condensed version. All right, so the only difference is the replacement of the hydroxyl groups with the chloro groups. So DCI is dichloroisoproterenol and ISO is isoproterenol. DCI has 2 chlorines where ISO has 2 hydroxyl group. DCI is a beta adrenergic blocker while ISO is a beta adrenergic agonist. And we probably should have said that DCI is mainly a blocker, because we see here that it's a partial beta agonist, right? So, but what we're pointing out here are, the differences, right? So one can be a blocker, the other is an agonist. So our follow-up question 2 says, draw the R and the S isomer for any aryl ethanol amine blocker, right? So just choose one and draw the R and the S isomer of any of these blockers. All right, so from our chemistry, we're familiar, or should be familiar, with Cahn-Ingold pre-log priority. And based on our follow-up question that we just saw, that is what you would use to assign the priority. And that, of course, is based on atomic number, right? So because of the insertion of an oxygen atom in the side chain of the aryl oxy propanol amines, the Canning-Gold pre-log priority of the substituents around the asymmetric carbon differs from the agonist, right? So the fact that we have an oxygen here makes the priority assignment different. So I hope you take that into consideration going forward, because if this is our chiral center, right, and perhaps I should draw that out. So I'm gonna just take the time to draw that out, right? So we have our hydroxyl group, and we have our carbon that is bonded to a nitrogen, and we have a carbon that is bonded to an oxygen, right? And then we have our hydrogen, right? So this is the carbon, for example, that is bonded to our nitrogen, and this is the carbon that's bonded to our oxygen, right? For the aryl ethanol amines, then the priority would have been 1, of course, here, and then 2 here, and then 3 here, right? And that is how we would have gotten the R conformation. And for the aryl oxypropanol amines, right, that priority is different. So it would be 1, 2, and 3. So that is the point that we're making. So even though I didn't draw the, the wedge or the hash, with the hydrogen, etc., right? So that is how you should draw it when you're drawing a 3D structure. I'm just trying to explain here that the priorities change for the oxypropanol amines. All right, so just to reinforce what I was saying, because of the insertion of an oxygen atom in the side chain of the aryl oxypropanol amines, the Canning-Gold pre-log priority of the substituents around the asymmetric carbon differs from the agonist. The pharmacologically more active enantiomer of beta blockers interacts with the receptor recognition sites in the same manner as that of the agonist, right? So in spite of the fact that nearly all of the beta blocking activity resides in one enantiomer, propranolol and most other beta blockers are clinically used as racemic mixtures, right? So as we have seen before, even though one enantiomer is the one that we are interested in because that is the enantiomer that has the activity, when you take this drug, what you take is a racemic mixture, so it has both the enantiomers. So propranolol in particular is one of these that are produced as racemic mixtures. So propranolol, and if we look at the structure here, it is one of those aryl oxypropanol amines, right? So it has become one of the most thoroughly studied and widely used drugs in this therapeutic armamentarium. It is the standard against which all other beta blockers are compared. So this is the boss drug right here for beta blockers. So it is the most lipophilic drug, right? So let's look at the structure. Yes, we have a hydroxyl, but for the most part we have saturation, right? We have the alkyl group, alkyl, and alkyl groups here, or lipophilic groups here. So it is the most lipophilic drug among the available beta blockers, and thus it enters the CNS much better than the less lipophilic drugs such as antenolol or nadolol. And so the use of lipophilic beta blockers such as propranolol has been associated with more CNS side effects. So these are the side effects of, CNS activity. So dizziness, confusion, depression, right? So if you take these beta blockers and you find yourself feeling this way, think to yourself that, okay, it's just a side effect of the beta blocker. It's not me, it's them. All right, so these side effects can be avoided, however, with the use of hydrophilic drugs such as antenolol or nadolol, right? So this is an important slide because it gives us additional information. It's saying, when a drug is lipophilic, it crosses that barrier, and so it can have side effects that you wouldn't desire, right? To avoid that, you can have a similar type of drug but make it more hydrophilic so that it won't have those CNS side effects. So this should be your thinking going forward when you look at the structure of a drug. All right, so one common structural feature of many cardio-selective beta blockers is the presence of a para-substituent of sufficient size on the aromatic ring along with the absence of meta-substituents. So Propranolol is the prototypical example of a beta 1 blocker of this structural type. So this is our beta 1 blocker here, Propranolol. And as I said, it's a para substituent here. So we have our aromatic ring or group here, and this group here, which is our amide group, is arranged para to this S ether group up here, right? And so that gives it cardio-selectivity. So it was the first cardio-selective beta 1 blocker to be used in humans because it produced several toxic effects. However, it is no longer in general use in most countries. All right, so we're just going to look at some examples of, first generation, second generation, and third generation beta blockers. So the first generation beta blockers were non-selective. So propranolol, nadolol, all of these alls, right? First generation non-selective. So what you want to do is, we should have an idea of the structure of propranolol, right? Because that is the drug, the prototypical drug, right? So we need to have an idea of the structure of propranolol. For the others, you just need to have an idea of their names and which category they fall under, right? So clearly I wouldn't ask you to draw their structures, but you need to have an idea of the class, right? Of the class of drug I'm speaking of is oxyaryl propanol amine. Yeah. So whether it falls in that category or not, or it's a ethanol amine, yeah, let's look at that and look at the similarities in the structure and make those kinds of observations and also their activity. So as we can see here, it's mostly anti-hypertensive or anti-glaucoma as the activity of our non-selective beta blockers, which are first generation. And then we have our beta 1 selective blockers, which are second generation. So we are familiar, or should be familiar, with antenolol, which we have seen several times. The name has come up well, so far, on this slide, nadolol and propranolol has come up already, right? Right? Right. So this is the structure of nadolol. And on this side, I think antenolol is probably the only one that has come up already. And this is the structure, and it's a beta 1 selective blocker. So guys, let's look at the structure. What's going on here? So the substituents are arranged parallel to each other, and of course we have the bulky group on the amine here, which, as you would have known previously, helps with the interaction or the selectivity towards the beta blockers. And clearly that's working out because they're beta 1 selective blockers. And for our beta blockers with alpha 1 antagonist activity, right? These are third generation. So several drugs have been developed that possess both beta and alpha receptor blocking activities within the same molecule. So two examples that we have here, labetalol and carvedilol or dilol. The structures are here. So as in the case of dobutamine, which we have mentioned before, the aryl alkyl group with nearby methyl group in these molecules is responsible for its alpha 1 blocking activity. So if you don't remember dobutamine, check that out, right? Go back and look at the structure. The bulky nitrogen substituents and another substituent aromatic ring are responsible for its beta blocking activity. So we know this already. The bulky nitrogen substituent, other substituents on the aromatic ring gives it its beta blocking activity. So these are two examples of beta blockers with alpha 1 antagonist activity, and they are third generation. All right, so our final set of questions for this lecture is here. So question 3 says, categorize the list of drugs below as either first generation, second, or third generation, right? So we have propranolol, antenolol, carvedilol or dilol, bisoprolol, nadolol, and labetalol, right? So we have 6 drugs and we have 6 names. So what are they? First, second, or third generation? Try to remember it though. Try to recall at least, you should know by now propranolol, antenolol, and maybe these 2. Well, you should have an idea of most of them by now. All right, so if you answered propranolol and nadolol as first generation, you would have been correct. If you had antenolol and bisoprolol as second generation, you would have been correct. If you had carvedilol and labetalol as third generation, then you would have had it correct. And so our final follow-up question for this lecture is, compare the structure and activity of dobutamine and labetalol. So draw the structures and look at their activity and comment on the differences. All right. So thanks so much for watching. See you next time.